Hello, now I will talk about the Navier equation for creating mesh. This is I will explain one of the source code of step 57 of the deal2 package. I am Asif Istiak from Mechanical Design Engineering, and this is a course of Advanced Numerical Analysis supervised by Professor Sijo Kim. So in this video I will talk about the a short description of the Navier Stokes, the explanation of Navier Stokes behind the code, and I will explain the codes, how it is built, and actually I will interpret all the codes here, and also I will run uh, the code and get the solution. Also for visualization I will use the visit software, and also I will change the source code. Let's say for example this can be changed into 2D to 3D or something like that. So in this case we will get the 2D and 3D too, and I will change the mesh here in the source code, and also I will demonstrate how the change of the Reynolds number affects the mesh. In the documentation we can get the explanation here, but I will briefly explain it. In the Navier equation, um, here in this case actually the flow that they consider here is assumed to be steady, and in a domain of omega, which is depends on the Reynolds number, and the diameter of the Reynolds number is 2 to 3, and the piecewise smooth boundary, and here you can see the F, which is defined as a force field, and here U, which is the velocity field, and the P is the pressure field. Okay. Well, unlike the Stokes equation, there are also demonstration in Stokes equation in step 22. But this in that term, the convective part was the U dot del U. So the first step of computing numerical solution is linearize the system, and this will be done using the Newton's method. A time-dependent problem is also discussed in maybe step 35, where the system was linearized using solution from the last time step, and no nonlinear solve is necessary. So what about the cases for linearization? So they define a nonlinear function whose root is solution of Navier-Stokes equation by this equation. So assuming the initial guess is good for to guarantee the convergence of Newton's iteration, denoting x of this x actually, yeah, this x will be dependent on the velocity and the pressure. So in that case the Newton's iteration on a vector function can be defined like that. And if here x to the power k plus 1 is the approximate solution, where k is, where the k is the step here, and I'm sorry, k plus 1, actually k plus 1 is a step here, and this x to the power k represents the solution from the previous step, and this part is the Jacobian matrix evaluated at the x to the power k, and a similar iteration can also be found maybe uh, we can find in step 15. Okay, so the Newton iteration formula implies that new solution is obtained by adding an update term to the old solution. So instead of evaluating the Jacobian matrix uh, and taking it in inverse, which is very complicated, so we can consider the update term as whole as update term like the others. So the final linearization system will be like this one. So here the UK and the yeah the PK are the solution from the previous iteration. Additionally, the right hand side here, this right hand side of the second equation, no, I'm sorry, yeah, this right hand side of the second equation is not zero, since the discrete solution is not exactly divergence free, and the right hand side here acts as a correction which leads the discrete solution of the velocity to the divergence free along Newton's iteration. So in the linear system, the only unknown of the part is this one and this one. These are the unknown part. Then we can use a similar strategy like the step 22, and now the Newton's iteration can be used to solve the uh, initialization, maybe for initial guess for u naught for this one, and p naught, and the tolerance also, and linear solve to compute the update term, to update this term uk and del pk. Okay, and also we can update the approximation like that, this one, so we can get instead of this we can get the velocity or the pressure, or yeah, between these two, and also we can check the residual norm. Well, for the initial case, yeah, the initial case needs to be close enough to the solution of the Newton's method to convergence. Hence, finding a good starting of the value is very crucial. So here B, yeah, here B in the velocity is very large. A good initial guess can be obtained by solving the Stokes equation with the velocity. So with the problem dependent, so this works. The B is greater greater or equal than 1 by 400 for the solution considered here. So however, the convection term here will be dominant in the velocity if this convecting term actually will be dominant when the velocity is small, because if the velocity is small, then convection will be increased, and in that case what about the velocity? So the velocity would be it would be like, it tends to 1 by, so I'm sorry, so there would be some criteria of laminar and turbulent flow, and if we get the laminar flow, then we can get the convective term too. So in that case too, in this situation we use the continuation method to set up a series of auxiliary Navier Stokes with viscosity approaching to one of the target of Navier Stokes. So yeah, though the initial gauges are something different, but yeah, the final gauge would be like that. In this process, the repeated sequence of viscosities Vi and that determined experimentally, so that the final solution can used as a starting gauge of Newton iteration. So what about the preconditioner and the solver? So at each step of the Newton's iteration, The problem results in solving saddle. There would be some saddle point like that. So this is the sparse matrix, and like the previous equation, uh, based on the previous equation, this is quite like the same. And okay, so last of all, the test case here. So we use the lead-driven cavity flow as for the case in the previous ones. Um, the computational domain in the actually, yeah, there are some examples of this type of cavity flow in the previous steps. The computational domain is the unit square, and the right hand side is f is equal to 0. So from that condition, obviously, if y is equal to 1, then we will get this condition, and otherwise we will get that condition. So in the code we will apply the if or else. And so when we will solve this problem, the error consists of nonlinear error, and the nonlinear parts decreases with each Newtonian iteration, and discretization error reduces the mesh refinement. So in this example, actually the solution from the coarse mesh is transferred to successively finer meshes and used as the initial guess. Therefore the nonlinear error is always brought below the tolerance of Newton's iteration, and the discretization error is reduced with each mesh refinement. So here the cavity refinement of Reynolds number, they have considered um, two types of Reynolds number. First of all is 400, and second of all is uh, 7500. So for these two Reynolds number, um, the viscosity actually defined on the Reynolds number, obviously. Uh, if the Reynolds number is 400, then viscosity will be 1 by 400, and even though we can still find a solution for Reynolds number 10,002, and the references contain the results of comparison, so we can uh, limit the discussion here just for the 700 and 7500. This is because the solution is no longer stationary, starting around 8000, but instead of becomes periodic for details. So now I will show the code here in their documentation. This is the code for 57. I will briefly discuss the code base here. So instead of, yeah, they have used the namespace of for the 57, and use the template of and the template's name is team, which is a class template, and there are the member variable and the member function. Okay, so the member variable are 1 2 3 4 5 6 7 8 9 10 11 12 13 14, yeah, like 14, and we can get the members too. uh, this class actually manages the matrices and vectors described in the introduction, and in particular the block vector for the current solution, current Newton update, and line search update. So for the boundary values in the right side, in this problem, the velocity along the upper surface of the cavity to be 1 and 0. Yeah, 1 and 0, and also the, this value will be on the other three walls too. So the right hand side function is 0, so we do not need to set the right side function in here. So the number of the components of the boundary functions is here. So the number of the if I set the dimension 2, then the number of the components will be 3 and something like that. So the ultimate use of vector tools here. So later the ultimate use of vector tools interpolation boundary values to set the boundary values, which requires the boundary value functions to have the same number of components as the solution, even if they are not used. Okay. So how about the preconditioner? Yeah. This portion is for the preconditioner, where the viscosity, uh, sparse matrix, pressure, and the inverse sparse matrix are uh, described here. So as per the theory, the preconditioner is an iterative method which is implemented as a matrix vector operator actually. So in practice, the preconditioner is decomposed as a product of three matrices. So here the three matrices can be the inverse matrix, A inverse. The first vector involves with a solve of the linear system, and here the system via the direct solver for simplicity also. And this sparse matrix is the star component on the theory the preconditioner is dependent on, and we will go through the class preconditioner here. So we can notice the initializer of the inverse of the matrix at the top left corner, and is completed in the constructor. So matrix vector will be like this. So how about the stationary class implementation? Yeah, here. So here, like the step 22, the Lagrangian coefficient gamma is uh, declared here, and also we can get the degree of freedoms, and how we can detect the degree of freedoms with the DOF handler. Actually, it enumerates the degree of freedoms and constrains the current mesh. Okay. So if I go in details, then for the yeah for the DOF handler of distributor of this line, actually the first step of associate of degree of freedom are given a mesh. Then this output, uh, we renumber the components to have the velocity of degree of freedom. Yeah, here that actually comes before the pressure degree of freedom to able to split the solution vector in two blocks. And then the Newton schemes that will be applied for the boundary condition to make sure the boundary condition remain satisfied during Newton's iteration. Okay. Similar to step 22, the conditions are yeah, stated here for getting the refined meshes. So we can get the local matrix, yeah, Reynolds number, degree of freedoms, and the matrix, and also the system Reynolds number. Also, if it these condition didn't satisfied, then it will print this one. Okay, let's get to the solver equation. Here the solver equation they use as solver control, yeah, that's a solver matrix. So if we have other types of the tools for visualization, such as the NVIDIA, then we can also get the we can also follow the parallel solver too. So in solving the parallel solver, it needs the very strong system. So yep. In this condition, this solver is used. And how about the Navier Stokes? Yeah, the refined mesh. The refined mesh is the conditions for the refined mesh are described in this section, and also for the Newtonian iteration the conditions are set here. So what are the conditions? The conditions they set here the degree of freedom, and they initialize the system and present solution. And in the first system they have this called the assemble system too. So in the first step, if this doesn't if this is not true, then it will print the this portion. And what is about the Newtonian's iteration? So if we want to get the Newtonian's get the knowledge about Newton iteration, we can get to the documentation, and this is actually the arguments for that. First argument will be yeah, defined here, and if it doesn't applies, then we will get to the else value. However, let's get to the run option. Well, in the run option, we have they have considered the Reynolds number 1000. So with that 1000, this will be run, and the Newton iteration will check whether it's true or not. And also we can change the refine mesh number. So here the mesh number is 5. So if we just click here and press 2, then it will be 60. And if we press here the 4, then it will get 256. Now we will get 124. Yeah, 124 meshes maybe. And also the viscosity is dependent on the Reynolds number here. So for stationary Navier Stokes, if we define the dim is equal to 2, and then we can get the results from the int uh, int main portion. So how about the result here? They have demonstrated the results here actually. The results for the low Reynolds number, the residual, this is the table, and they have mentioned the velocity and magnitude here. So the solution is compared with the this solution, and also the horizontal velocity versus the y coordinate. And for the high Reynolds number, the loss code convergence is like that for total iteration. Here the horizontal velocity is quite different. In the initially this dropped, but in the laminar or in the lower Reynolds number, it was developed consequently. And this is the velocity magnitude, which is more dense here. Like that. For 57, so we can go to that folder. I have already make it and run it. So here is the command. First I have cmake it, then after cmaking it I have make it, so it was 100% with run made, and then I have write dot slash step 57, and this has completely run, and these are the, you can see there are adaptive meshes here, and you can see the steps and the number of the lines on the each, and here after running you can get, I have used visit for visualization, and you can get the files. Here are almost a lot of BTK files. So how we can see it? We can visualize it by visit. Here we are going to visualize by visit, and I have to select it, and all the BTK file will be selected. Then I will go to the shadow color to make a color and draw it, and this is the basically 2D. And if I wanna add some meshes here, then and also the contour, this is the contour for the velocity magnitude, and also for mesh we can draw that, and for velocity magnitude these are the velocity magnitude contour. And I don't need this type of annotation, so I will close the annotation here. Okay, let's skip it. Then what can we do more for good visualization? So I will elevate that, always apply yes and dismiss, and I will draw it. So here you can see the elevated velocity magnitude, the velocity contour here. So if I play it, how it will look like. So yeah, there's some bugs maybe. Some plots had errors, so visit while regenerate these plots. Okay. Okay, so these are pretty nice to see it, and we can delete the annotation, like no annotation. There's some problem in my screen, so I will fully extend the screen and apply and dismiss. So here are the velocity contour of the Navier-Stokes equations, the finite limit analysis. Okay, thank you. So now I will discuss about the change if I change of the result if I change the source code of step 57. So if I click it here, then this is the code source code for step 27. So in that case, uh, I will try to see the results if we change the Reynolds number. So this is the viscosity. The Reynolds number is 7500. So I am applying here 400. Okay. And why not changing the refine mesh in the run section? So this is the run section. Yeah, this is the run section. So I will change the mesh, like I will change it to 4. Now I'll save it and let's make it again. I'm deleting the files that I had run before. Now I'm sorry, the terminal, we will see make it, then make it. So it is completely executable, and now after completing the making, I will press the executable file here, dot slash step 57. So let it be finished. So this is run completely, and I will go to the visit. I will go to the visit for visualizing. We will observe how the result has been changed. So if I click it here, then apply the velocity magnitude and draw it. So this is quite different. In the previous case, the higher velocity we have got from this area, but in this case the velocity has been decreased here significantly. So how about elevating this one? If I elevate this one, this is totally different from the others, because the Reynolds number has been changed, and is I have input in a laminar condition, and so we can also add the mesh here. Yeah, thank you. Now we can compare that since there was a difference between the Reynolds number and so for the velocity, so the ultimate result would be different like this. So this is basically the difference here for the Reynolds number 7500. Uh, the 2D, you can see the difference of the 2D of the velocity contour, and also the mesh has been changed too. And for the Reynolds number, one of the significant changes I can observe that there is a huge amount of vortex, but in this case the vortex is quite low for the velocity of the for the less velocity. So from here we have learned that how to modify the source code for the Navier Stokes equations, the basic behind the code and how to code it, and all the important aspects of the code, and difference for the Reynolds difference of the results for the difference of the Reynolds number. And thank you.